So first of all, the YouTube live link is, I just shared it. I will share it on Telegram also. Okay, so again, good morning, everybody. So now about this honor code that I was talking to you about. So let me repeat it again, what I mean by the honor code. The honor code is a voluntary, self-enforced code of conduct. Okay, that means nobody is going to be there sitting on top of your head, watching you to make sure that you are following it. That is why it is called a honor code, right? It is upon your own honor to follow this code. Okay, so what is this code? It is the statement that you will not use any unfair means to gain an advantage over your classmates in any assignments, quizzes, or tests. Okay, that is basically the honor code. And now, given the circumstances, the Zoom classes and all, right? We don't have any way to enforce this code, right? It's up to you. If you choose not to follow it, there's nothing I can do about that, right? That is why it's called a honor code. That means, right? In Hindi, that would be called, I don't know, Maryada or something like that. I don't know the correct translation for it, right? So, do you have any doubts? If you have any doubts or if you don't understand what I'm talking about, please raise your hand. So if you don't have any questions or any doubts, then I will assume that all of you understand and agree to follow this honor code. Okay, so this is the basis of the conduct of our class. All right. All right. Now, there have been some questions about how to study for the for some of the classes in the course and all that. Okay. Now let me just show you the course plan once. Right. So this is the course plan. Right. Now you can see that here, for example, special relativity. Right. We start off with swimmers in a river, Michaels and Morley, and so on. Now you can see that in the references column, it is listed clearly what are the relevant sections and which is the relevant book. So KK refers to Kenneth Crane. Okay. If you look in mechanics, for instance, KP is the only one where there's a different K that refers to Kleffner and Kollenkow. And for mechanics, also the sections are clearly outlined, chapter 1.1 to 1.6 and 2.1 to 2.4. Okay. So somebody had a question about how they should study for exams and tests and all. Now, first of all, this is not, we are not running a coaching class, right? This is college. So you have to, we will not give you a page by page or point by point guide of how to study and what to study. Okay. But even then, this is a very clear, this is very clear on which sections are relevant for you, right? Now, so it is, you know, as far as I can see, it is a guide to what to study, right? Apart from that, of course, you have my lectures, and then, like I said, the problems that I give you in class, those will be your self-study problems. Okay. Now that doesn't mean that those problems cannot appear on the quiz or on the test. Okay. Please keep in mind that if I give you a problem, and even if I don't give you a problem, it can be on this or test. Okay, because this is again not a coaching class, right? So, so it is very important that you do these problems, and that if you have any difficulty in solving these problems, that you either put a question on Moodle and some people have posted a couple of questions. Nothing about any of the homework problems yet so far. All right. Then, so this point I just wanted to clear. Are there any questions about this issue? Any questions? You can please just speak up if you have any questions. Okay. Okay. So I will get started with the actual class. So how much time do I have? Can I take till 12? Excuse me, till 12:15 or so?
Yes, sir, you can.
Okay, you don't have a class right after, okay? I
Yes.
think. Oh, good. All right. So, we talked about this uh, this wave equation, and this is the sign error that I mentioned to you, right? So, so what was the let's just go over it. So in the last class, I talked about the relativity principle. That's a statement that the laws of physics are the same for all inertial observers, right? And the key word here is inertial. I'll explain what that means today. And if this is not the case, what is the consequence? The consequence will be that an observer can determine their own state of motion or state of rest, right? Absolute state of motion by seeing how, by conducting an experiment in their own frame of reference and by comparing it to the results of the same experiment conducted by another person in a real frame of reference and comparing the results, right? Uh, so this is an example that I gave you uh, that, for instance, one can look at something, any law of physics, it doesn't matter which law, right? So if there is a violation of the relativity principle, then, so if the relativity principle is obeyed, then that will mean that all laws will stay the same, right? Conversely, on the other hand, if the relativity principle is violated, then that means that none of the laws will remain invariant under change of state of motion, right? So you can take any law. You can take, for instance, Newton's second law applied to a spring, right? And so the prediction is that the spring with the same mass and the same spring constant should oscillate with a fixed frequency omega. So if the relativity principle is violated, then one can maybe, this is an assumption. Again, we can't say that, well, this is what would happen. This is how the relativity principle would be violated. But if it was violated, then one way in which it could be violated is that your oscillation frequency could be some function of your state of motion, your absolute state of motion, right? So if you know what your, if you compare your oscillation frequency to that of other observers, right, then you can determine the functional form of this dependence on the state of motion, right? And depending on what value you observe and the functional form, you can. So as an example, just as an illustration, this is purely like hypothetical, is that you could have something like this. Let's say that if your absolute velocity is your x-axis, and this is your, this would be something like, let's say, delta omega. Delta omega would be the variance in omega from omega naught, right? Omega naught is just expected velocity, angular velocity, root k by n. So this delta omega could be something like this, right? It would start off at 0 for absolute state of rest, and then it could go and increase to something like this. Let's say, okay, again, like I said, this is some hypothetical situation like this. Let's say. Now, so if you find that in your own frame of reference, you measure the angular velocity of your spring to be given by this point, which I've labeled with a cross, right? Then if you know the functional form, if you know the form of this curve, then you can extrapolate backwards and you can determine what your velocity is, absolute velocity is, right? It's v prime, whatever that is, which is the corresponding value for this, right? So this is just one hypothetical example of how the violation of relativity principle can allow you to determine your absolute state of motion, right? Then another way in which this can work is that if you look at another set of laws which are Maxwell's equations. In Maxwell's equations, you have electric and magnetic fields, and we know that these electric and magnetic fields they will obey this relationship. This is called the wave equation. And in this wave equation, there is a constant c, which is related to the two other constants by this relationship. C is equal to 1 by root of mu naught epsilon. And mu and epsilon are respectively, they're called the magnetic permeability and the electric permittivity, right, of the vacuum. Now, again, if the relativity principle is violated, one can maybe assume, one can again make a hypothesis that, and again, if at any point you don't understand anything that I say, for instance, if I make a use of word like hypothetical and you don't know what hypothetical or hypothesis, you ask, okay, don't be ashamed or embarrassed because you don't know, you think you don't know this term, it's okay. All right. Or if you don't want to ask it in public, you can always put it in the private chat in Zoom, right? Like, sir, what is hypothetical? Okay. So hypothetical means, just something made up, okay, not real. That's the simplest explanation. So if we assume that this mu and epsilon depends in some way on the state of motion, then this c will also be some function of your absolute state of motion. And then by measuring the speed of light in your own frame of reference and comparing it to the speed of light again as it would be seen in a state of absolute rest. So once again, we can have something like this. This is the y-axis is the let's say the velocity, your absolute velocity with respect to the unmoving vacuum, right? Newton's concept of an unmoving vacuum. And this is, let's say, the delta c meaning the change in the velocity in this function c, right? And again, this could be something, I don't know what it could be. It could be anything, right? This is just a hypothetical change. So if you find that you measure delta c in your frame of reference to be some value, you can trace it back to determine what your own absolute velocity is, right? Now, so what was done, right, was this experiment was conducted around the year around the year 1886, I believe. It's called the Michelson-Morley experiment. Okay, and I think the best best thing I can do is to show you illustration. 1 second. So share screen. Okay, so you can see my screen, right? This is Crane. This is Kenneth Crane, the book, right? This is a photo of one of the people who conducted the experiment, Albert Michelson. And the experiment that they conducted was performed in 1887, right? And this is an illustration of the experimental apparatus. Okay, so this is a block of metal or of lead, and this is very heavy. Okay, it's like, I don't know how much exactly, but must weigh like several tens of kgs. And then this platform was placed on top. It was mounted on a 1.5 meter square stone slab floating in a pool of mercury. Right. So you know that mercury is a liquid at room temperatures, right? It is what is used in the old mercury thermometers, for example. So this thing is placed on top of something else, which is floating on top of mercury. The reason for that is so that you can isolate the apparatus from any vibration. Now, what are all these different things? So this is an experiment in optics. All right. So these are the various components. You have a light source, which is S. So this is the schematic diagram. Hello, am I still connected? Can you all hear me?
Yes, sir.
Yes, sir, we can
Yes,
hear
sir,
you.
we could hear you.
Okay. So this is the light source. A beam of light goes from S, okay? And this over here, this is called a half silvered mirror, okay? So now you know that, I don't know if you know, but a mirror is nothing more than a piece of glass, right? You just take a piece of glass, and on one side of the glass, you put a silver coating. And because of the properties of that coating, the light which comes in is reflected, and so that piece of glass becomes a mirror when seen from one side, right? Now the thing is that you can make that coating, you can make it a partial coating instead of making it a full coating, so that 50% of the light that falls on the surface of the glass is reflected and 50% is transmitted. Okay, and such a glass is called a half silvered mirror, and it's also known as a beam splitter, right? Because what will happen is that if any beam of light falls on this mirror, 50% will be reflected and 50% will be transmitted. So from the original beam, you will get two different beams, right? The beam will split. You get a beam splitter. So you have a beam of light that goes in one direction, and then this is a regular mirror. This is also another just a mirror. This beam of light is reflected back. Then this beam of light is also reflected back, right? So they both follow different paths, which are at 90 degrees to each other. That is the purpose of this apparatus. Then these two beams of light, they come together, and there is some lens which collects the light, and there is a screen on which you can see the results. Now, this sort of a apparatus is called an interferometer. Okay, so it's called a interferometer because what it does is it measures the interference between these two beams of light. Okay, and uh, what was the purpose of this experiment? Okay, the purpose was that uh, so this illustration is shown in again in Kenneth Crane in example 2.3. This is the uh, question of swimmers in a moving river. Okay, so you imagine that there is a river that is flowing. Okay, and I'll explain in 1 second what this river is meant to be. And in this river, you have people who are swimming. Now, the river is flowing in one direction, right? Let's say from left to right. Then you have a swimmer here over in the first picture who is swimming upstream and downstream. Okay, so against the current and then with the current. And then in the second picture, you have a swimmer who is going across the river and back up. Okay. Now the question is that we have some observer who is sitting on a floating raft, let's say O prime. Okay. So a swimmer capable of swimming at a speed c in still water. So c is the speed of the swimmer in still water. That means if the water was not moving, the swimmer's speed is c. Now, since the water is flowing, what will happen is when the swimmer goes upstream against the water, what will be the speed of this swimmer as seen by an observer on the river? It will be u minus c. Do you see that?
Yes, sir.
And similarly, if when the swimmer is moving downstream, the speed of this swimmer will be u plus c. Okay. Now, suppose the swimmer swims upstream a distance L and then downstream to the starting point. So the swimmer starts from the same point in both cases. Now let me show you my notes. Okay. So we have this picture where we have a swimmer starting from the same point. Okay. First, the swimmer goes up and then down. And then you ask, what is the amount of time it takes for the swimmer to return to the same point? Okay. And then in the second case, the swimmer goes downstream and then upstream. And then again, you ask the same question. How much time does it take for the swimmer to go down, go around this path and come back to the same point? Okay. So let's say let's call this delta t perpendicular and we'll call this delta t parallel or anti-parallel, because this is your river and your river is moving in this direction with some speed, let's say u naught. Okay. So let's look at delta t parallel first. So what is delta t parallel? Okay. So in both cases, the swimmer goes a distance L. Here is L and here is L. So in delta t parallel, what will you get? When the swimmer goes downstream, the velocity of the swimmer going downstream is u naught plus c. Coming back upstream, it's u naught minus c. Okay. So what will be the total time that is taken? The total time will be L over u naught plus c and L over u naught minus c. This will be the time taken by the swimmer, right, for upstream and downstream. And what is this? This is you can do a simple calculation. You'll get you can take L common, and then in the denominator you'll get u square minus c square, and in the numerator you will get 2 times u naught. Okay. Now we will rewrite this a little bit differently. I will take a factor of c out of the numerator, out of the denominator. And so this will be written in the following way. Okay. Right. This should be, sorry, this should be c minus u naught. Right. C. So this will be 2ac. So I take a factor of c square common from the denominator, and I get 2l by 2l by c 1 over 1 minus u square by c square. Okay. And why do we take this to be c minus u naught? Because the assumption here is that the speed of the swimmer, right? The speed of the swimmer, which is c, must be greater than the speed of the river, right?
Yes, sir.
Because if it is not larger than the speed of the river, then the swimmer will never be able to return to the same point, right?
Yes, sir.
No matter how fast the swimmer goes, the stream will always take them further away. Okay. So this is the time taken for the swimmer to go up parallel in this direction, up and downstream. Okay. Now one can ask the same question for the perpendicular direction. Okay. So now what we want is, we want the swimmer, so this is the river. The river is flowing like this, right? Now, if you are a swimmer and you start off moving in a direction that is perpendicular to the river, what will happen? And you are moving with some speed c, all right? And the river is moving with some speed u naught. What will happen? You will move with some velocity in this direction, right? And this velocity will be u naught square plus c square. And then what will be your trajectory? Your trajectory will be this, like this, right? So you will end up over here. You will not end up at the same point where you started off, right? So if you want to end up at the same point where you started, right? Then what do you have to do? You have to ask what is the speed. So you need to be moving in this direction, right? You can't move straight up. You have to move in this direction. Okay, and my Zoom connection is being very strange. Okay, can you see the screen now?
Yes, sir.
It's being a little bit slow to update. Well, it's not updating on, okay, now it's updating. So you have to move in a diagonal direction, Not updating faster. Okay, so you have to move in a diagonal direction such that you have a velocity in the direction opposing the stream, and you're moving at a velocity minus u naught in the horizontal direction. Because if you don't have this velocity, right, in the horizontal direction, then you will always drift down the stream. But you don't want to drift down the stream, you want to go up and then come back down. So you need to have this velocity in the x direction to counter the velocity of the stream. Okay. And now, what is your actual, what is your velocity with respect to the still water? It is c, right? So this velocity, your tangential velocity over here, this is going to be c. So what is your velocity with respect to the river, right? With respect to the river, your velocity is going to be c square minus u naught, which is this perpendicular component. Okay.
So once, can you repeat, sir?
Okay. So you want to go upstream and then downstream.
Yes, sir.
Now, if you just start moving in a direction perpendicular to the water to begin with, what will happen?
I will drift, sir, to the right.
You will drift. So you want to move in a direction diagonal,
Yes, sir.
and you want to have a horizontal or tangential velocity which
Minus u naught.
opposes the speed of the water, right?
Yes, sir.
Right. And then what is your own velocity at the rate at which you move? That is c. Right?
Sure,
If you consider how many strokes per second you can make, that
Yeah.
is a constant, right?
Now understood, sir.
Okay, good. So your effective velocity going up and down is this root c minus c square minus. So what is delta t perpendicular going to be?
2 into L by root over c square minus u square.
2L divided by root of c square minus u. Again, I will take one factor of c out of the denominator, and I will write it like this. So these are my two different values for the time, for the return time. And they are different, they are not the same. Okay, now what does this have to do with the Michelson-Morley experiment? The Michelson-Morley experiment, as I showed you in that diagram, involves a beam of light. And this beam of light is our swimmer moving at some speed c. Now, the beam of light goes in two different directions. One is up and down, and one is front and back like this. And then these two beams come and meet, and what will happen? There will be interference between these two beams, right? Now, we have taken the length, the experiment is designed so that the length of these two arms is the same. Okay. The length of these two arms is the same. So if you are in the rest frame of this apparatus, what should happen? What should happen is that delta t parallel and delta t perpendicular should both be equal to 2L by c, right? And now you must keep in mind that light is a wave, right? Or when we say is, instead of saying it is something, we should say it behaves like a wave, right? Light behaves like a wave. How do we know this? We know this because of something called Young's double slit experiment, among many others. So this experiment shows us that light exhibits this phenomena of interference, and interference is a wave phenomenon. So we know that light behaves like a wave. So now this wave is split into two parts. Okay. And when it is split, at the moment that it is split, what will happen? The beam that is going in one direction and the beam that is going in the other direction, they both have the same phase. They are not out of phase, right? Because they are generated from the same original beam, right? Is this clear? Please ask at any point if you have any questions, okay? So these two rays of light starting off at the beam splitter, they have start off with the same phase. So one goes left, right, one goes up, down. They both come back and meet. Now, if the time taken to travel up, down, and left, right is the same, then they will continue to be in phase when they meet. And then here, what will happen is, so we will define another quantity, let's say small delta t, which is delta t parallel minus delta t perpendicular. Okay. So this is equal to 0 if these two times are the same, and if this is equal to 0, then there will be no interference. All right. There is no interference. On the other hand, if for some reason these two times are not the same, then you will observe some sort of interference. Okay. Now, why do we think that there should be some interference? Because this whole apparatus is placed this is the earth and this is the sun, obviously not drawn to scale. And on the earth, you have this apparatus, this Michelson-Morley apparatus. Right? And now the earth is moving around the sun at some very, very high speed, u0, let's say, okay? And the relative direction of the speed keeps changing. So after 4 months or after 3 months, right? After 3 months, that means quarter of a year, 1/4 of a year. The Earth's location is over here. And now what has happened is that the direction of the parallel and perpendicular arms has switched. Right? Here, if you say that your perpendicular arm and your parallel arm, let's call this the A arm and let's call this the B arm. Your A arm is the perpendicular arm and your B arm is the parallel arm. at this point. So let's say that this is January. And then you are in April. Now in April, what happens is your velocity is now in this direction. So your A arm becomes the parallel one, your B arm becomes the perpendicular one. Then another 3 months later, so that's May, June, July. What happens? Your A arm again becomes the perpendicular one, and your B arm again becomes the parallel one. Right? Now the direction of your velocity is reversed, but that will not affect anything. Right? Because once you go up and once you go down, so it doesn't, the effect cancels out. And then 3 more months later, so that's July, August, September, October. Okay, this is not a. Now what happens? Now again your parallel and perpendicular directions are switched. So this is the configuration that you have in January and in July. And this is the configuration that you have in April and October. Okay. So what will happen is, let us say that in January and July, you find delta t, this small delta t, that is the difference between the time it takes to go parallel and the time it takes to go perpendicular. Let's say this delta t is some value, let's say capital T naught. Then what will happen is, when you get to April and October, what will happen is delta t will become minus T naught, right?
Yes.
Because the parallel and perpendicular arms have switched. So these two numbers will exchange, right? So what should happen is that, see, what actually happens in an optical experiment is that there is no such thing as no interference. You always have some interference. So that means, let's say that in July or in January, and your interference pattern looks like this. It looks like a bunch of it basically looks like a bunch of dark lines and some bright regions. Okay, so this is your interference pattern in January. What you expect is that when you look at this by April, what should happen is, this interference pattern, it will shift a little bit. Okay, so there is a small shift over here. It's a very small shift, but it can be measured. This shift corresponds to the change of 2 T naught relative to January. When you come to to July, what will happen? The interference pattern will again shift back. So it will shift back by how much? By an amount minus 2 T naught. And again, when you come to October, the interference pattern will once again shift in this direction, right? So this is October. So if you repeat this experiment over the course of one whole year, you should observe your interference pattern shifting one way and then back to the original place, and then shifting the other direction and then back to the original place. Okay. And why is this interference pattern shifting? Can anybody tell me why there should be a shift?
Because of changing
Because
of
of?
arm changing.
No, that is fine, but why is that? Why does that changing of arms cause a shift in the interference pattern?
Because of change in phase difference, sir.
And why is that phase difference changing? Why is there a difference in the phase?
Due to the change
Why?
in direction of velocities.
Because we are making the assumption, right, that the motion of the light relative to the absolute vacuum, right? So we are saying that there is some absolute vacuum. There is some absolute state of rest. Relative to this absolute state of rest, the Earth is moving with some velocity u0. And so the results of your measurements depend on measurements on values of velocities measured with respect to your absolute vacuum, right? So according to this idea, the correct way to measure time intervals is not this. This is not the correct way. Instead, the correct way to measure time intervals is this one, according to the theory that there should be an absolute vacuum, an absolute state of rest. Okay. So according to this theory, there should be this interference, this change in the interference fringes. Now, what was observed? What was observed? The actual result was a null result. Right? So null result means that no such shift was observed. Okay, or there was some observed shift, but it was much too small to correspond to the velocity of the Earth. The velocity of the Earth u0 is something like, let's say, I don't know the exact. I always forget every semester I teach this class, and I always forget. What is it supposed to be? Right, it's supposed to be, let's say, 5 kilometers per second. No, sorry, not 5 kilometers per second. It's supposed to be.
So 3 kilometers per second.
No. Huh? How much?
3 kilometers.
No, not 3. It's more like 76 or 760 kilometers per second. So the velocity of the Earth around the solar system, if you just look at the radius of the Earth's orbit, you calculate the circumference, you take the amount of time it takes to go around once, right? You just divide the circumference by the time. That gives you the average speed of the Earth, right, as it orbits around it. So that average speed of the Earth is something like 760 kilometers per second. Okay, It's some large, huge number. But what Michelson and Morley observed was something that gave a velocity of the Earth as something around close to 5 kilometers per second at most. Okay. So that is why it's called a null result. I mean, that is within experimental this thing, within the realm of range of experimental error. And now the thing is that once you repeat the experiment for one whole year or for 6 months, then even that experimental error is cancelled out, right? And again, they obtain no change in the interference pattern. So the result is that as per Michelson and Morley, U naught is equal to 0. Okay. So what is the meaning of this U naught is equal to 0? It means that either there's something wrong with the apparatus, right? Obviously, that's the first question. So you check the apparatus, you have other people check it. Okay, no problem. Then you ask, is there something wrong with my theory? That's the next thing, right? Or no, then you ask, is there something wrong with my measurements? My apparatus might be working fine, but I might be making some systematic error. Also, there might be some random error. There are two kinds of error, right? Systematic and random. So if there is, so random error can be corrected by, again, checking, that basically involves checking the apparatus. And systematic error would arise due to the motion of the Earth, due to the location of the Earth in its orbit. So you average over the systematic error by looking at the observations for one whole year or for 6 months. So that way you account for when the motion is in one direction and when the motion is completely reversed. So that way you average over the systematic error, right? So if you still get a null result, then that means that what is happening? Why are we getting this result? So it was to explain this result that two physicists, one is called Fitzgerald and the other is called Lorentz. They proposed what is known as the Lorentz-Fitzgerald contraction. Okay, so they said that there is something that happens in matter due to the behavior of electromagnetism, something that happens, okay, we don't know what it is, such that when you have a piece of any matter and it has some length L0, then when you put this object in a moving frame of reference, okay, so now it is in some moving frame of reference, the apparent length of this object as measured by an observer at rest, the apparent length of the object becomes L0 multiplied by 1 minus u square by c square. Right? So they said that whenever, so I have some object, like I have a pen here. And I say the length of the pen in my frame of reference is L0. Now I give the pen to my friend, and that friend is in some vehicle or some spaceship which is moving at some high speed. So then the spaceship moves. This is the spaceship. It moves past me at some high speed, right? And the pen is inside this spaceship. As the pen moves past my position, I conduct an experiment asking what is the length of this pen as seen by me. So Lorentz and Fitzgerald, they said that, well, the length of the pen as seen by me, the length of the moving pen as seen by the observer at rest, is less than the length of less than its rest value. Now, u in this u is less than c, right? C is the speed of light. That's 3 times 10 to the 8 meters per second, 3 lakh kilometers per second, 3 lakh kilometers per second, right? That's a huge number. So whatever your rocket ship is going to be moving at a speed less than that. So that means u by c is less than 1, which means that this factor, right? So u by c square will also be less than 1. It will be much less than 1. Well, let's just keep it at less than 1. Then 1 minus u square will be less than 1. So this is a contraction, right? Because L naught is being multiplied by some factor, some number which is less than 1. So if you have this Lorentz-Fitzgerald contraction, then what will happen? Anybody?
Sir, we assumed the lengths of the arms may change, sir.
Exactly. The length of the arm is changing. But which arm?
The parallel arm, sir.
Parallel arm. The one which is moving along the direction of the velocity. And how much is it changing by? It is changing by so this is the original amount of original expected values of the perpendicular and parallel velocity times, and then you have the delta t parallel prime. Prime means with the Lorentz-Fitzgerald contraction taken into account. So this is L naught with the Lorentz-Fitzgerald contraction taken into account. This becomes 2L by C, not L naught, but 2L by C, 1 minus U naught by C square. And what is L? L is equal to L naught times 1 minus U square by C square, square root. Okay. So this, what is this? This is the Lorentz-Fitzgerald contraction. So what will this give me? I'll get exactly a factor of square root, which remaining in the denominator. Okay, delta t parallel prime. And this, now you can see, is going to be exactly equal to delta t perpendicular. Which means there is no interference, no phase change, right? Now you can ask an obvious question. What is the obvious question? Anybody?
What if it approaches the speed of light?
That is a question, but I don't think it's the most obvious question, simply because the physical feasibility of that was null.
Sir, but Earth is moving at that speed. There should be an interference, no, sir.
No, but like I said, the feasibility of that uh, possibility, right, is negligible. The physical feasibility of that possibility is negligible.
Then how were they able to observe the interference?
No, the obvious question that arises is why is it only the parallel on that contract? Right? Wouldn't that be the obvious question to ask? Why is it only the parallel arm? Why not the perpendicular arm? Yes? No? Anybody?
Yes.
Is that not the obvious? It's the obvious question to me. From my perspective, that would be the obvious question. So there are various reasons for why it should be the parallel arm. Okay, and these had to do with the behavior of electromagnetic fields with respect to moving observers. Okay, so people had looked at the equations of electromagnetism were published by Maxwell in which year? Maxwell published them in 1869, if I remember correctly. Or not 1869, I think 1863 or something. 1869 was, yeah, I think 18, something like this. You can check. So between 1863 and Michelson-Morley, which was 1887, there was a time of how much? About 24 years, right? In this time, people had thoroughly examined the behavior, the expected behavior of electromagnetic field. And what people found was that, what physicists found was that electromagnetic fields generally behaved in a way such that when you have an electron, for instance, an electron has some field, right? You have an electron, it has some electric field like this, right? It has some radially pointing electric field. So what they people asked is, well, if I have a moving electron, how does the field of a moving electron look like, right? And the field of a moving electron changes like this. It in the horizontal direction. So if this is the direction of motion, then in the horizontal direction it shrinks, and in the perpendicular direction, actually it's the other way around, but for the purposes of explanation, this is okay. In the horizontal direction, it appears to become more compact and remains the same in the perpendicular direction. So from this, they concluded that, well, what can happen is that something is causing the atoms to come closer together. Okay. So anyway, this is a very vague and rough justification for why it was only the perpendicular, why it was only the parallel part. But they had a justification for saying this based on the understanding of the behavior of electromagnetic fields in matter. Anyways, I'll stop here because I think people are starting to leave. I think maybe you have another class at 1 or so. So this was the Michelson-Morley experiment. And then we will talk about in the next class how the Michelson-Morley experiment led Einstein to the relativity principle and his theory. Okay. All right.
Yes, sir.
So
Yes, sir.
yeah, class is over. You can go. If you have questions, you can ask them.
Sir, according to the Lorentz Fitzgerald transformation, so if any object approaches the speed of light, at one point it is supposed to vanish, sir.
Okay. So what's the point? What are you trying to? What is the point that you're trying to make?
No, is that really what the equation states?
So okay. So first of all, as you approach the speed of light, it will become more and more difficult to change your speed. Okay.
Okay,
So the
okay.
speed of light, you can never approach the speed. You can never reach the speed of light. If you have a massive object will never be able to reach the speed of light because it takes an infinite amount of energy to reach the speed of light. Okay.
Yes, sir.
So that's the simplest answer. Is that, well, it won't happen. The second thing is, the second answer one could make is that, well, all expressions are approximate. They are valid only in some range of validity, right? So it's possible that as you actually go very close to the speed of light, there could be some other changes. There could be some other modifications to this equation, which would prevent this vanishing effect that you're talking about. Okay, but that would require us to modify Einstein's theory in some way. And again, there is no, unless we have any evidence or any reason to do that, we don't do that. Any other questions?
Sir,
And people, right, one second. If people have questions, they can also ask in the YouTube chat, okay? Yes, please.
the last day you said about a vector k in that kx minus omega t thing. I did not get that part, like vector k.
Okay, okay. I'll answer that, but first I'm just waiting for people to finish asking questions about today on TV. I'll come to that question, right? So, are there any other questions about today's material? Okay, well, if there are, you can ask me. In the meantime, I will answer Rajpita's question about what this vector k means. Okay. So let's look at the equation of a wave again. This is fx t is equal to a cosine kx minus omega t. Right? This is how we write down this equation. Now, what sort of object does this represent? Is it something that is only defined along the x-axis? Is it something that is only defined in one dimension? Right? I know that that is not the case because I know that waves are something that move in 2 dimensions and in 3 dimensions, right? So for instance, if you have a lake, if you have some water and you drop a stone in that water, what will happen? Waves are created like this, right? 2-dimensional disturbance. And then if you are in this is on the surface, it's two-dimensional. Now, if you are inside the water, that means if you are in the bulk, whether you are in water or in air, like I'm in air and I'm talking right now, the waves being generated are three-dimensional, right? They are propagating in different directions, right? They have an intensity that varies in space in all three directions and also in time, right? So the waves that we generally have, for example, this wave, these are waves that are some disturbances which are traveling in three dimensions. So what does this function represent? This function only refers to x. What about y and z? Okay. So you should actually look at this function as a function of x, y, z, and t, right? So this is some disturbance moving in three dimensions. The only thing is that the left side doesn't depend on y and z. Okay, so what does that mean? That means that if I look at any point, so this is my x-axis. If I look at for constant x, what am I looking at? I'm looking at the yz plane, right? This is the x is equal to constant surface. X is equal to constant will just be the yz plane, right? At a particular value of x. Then at another value of x, right? This is also an x is equal to constant surface, right?
Yes, sir.
So when I look at this wave, how should I interpret this wave? I should think of this as a phase angle. This is a phase. This is a phase, right? This is the angular part, right? This is the phase, and this phase is constant on the yz plane, right? So what is the phase here? Let's say for this plane, here I will have one phase, and on this plane I'll have a different phase. What will be the phase over here? The phase over here will be, let's say theta1 is equal to kx1 minus omega t1, where this is, or again at the same value of time. Okay, now we are looking at the whole system at a fixed value of time at different positions. So this is x1 at the time t, this is x2 at the time t. Here the phase is theta1, here the phase is theta2 is equal to kx2 minus omega. And this theta1 is the same for the whole plane, for all values of y and z which live on this plane. And here theta2 is a constant for all values of y and z which live on this plane. Okay, so you have the picture that your surfaces of constant phase, your surface of constant phase is a plane. So if I look at my wave, then the picture I get is that my wave is actually a set of planes like this. a set of surfaces like this. Right? And each surface, the phase is constant, but as I go from surface to surface, the phase changes. Fine. And what is the direction of, so this is called a plane wave. Where your surfaces of constant phase are planar surfaces. And what is the direction of propagation of your plane? The direction of propagation of your plane is going to be the normal vector to the surface of constant phase. So the direction of propagation of your plane is this, right? This is the velocity of your plane, right? Now you can get rid of any XYZ axis, okay? And you can just imagine taking this picture. You can just imagine taking this picture and rotating it in some way. Because your plane, your wave doesn't have to propagate only in the x-axis. No, your wave can propagate in any direction. No? Then what is this? This is the direction of velocity, the velocity vector of your plane, right? Vector v, not just
Yes.
vx, vector v.
That's why like we are using in all the planes, so we are using vector k.
So you get a vector k.
Okay, sir.
Got it?
Yes, sir.
So k represents the wave. The term for it is called a wave vector. K is equal to kx, ky, and kz. Now the angular velocity omega will be the same for all the k.
Yes.
Okay.
Sir, then if we think at like only a particular point of time means it will go in either one of the direction. It's not like that at particular time it's in all different directions.
Sorry.
Means at particular one point of time it will be either in any of the one of the three. It's not like that it will go around like in all the direction at the same point of time.
No, so that's not the right way to think about it. I'll give you another example. Let's say these are plane waves, right?
No, sir, I got this part.
One second. Maybe you got it, but what you said might have confused somebody else. So let me clarify. You can also have radial waves, right? What is a radial wave? A radial wave is, for example, the wave on an ocean surface like this. This is your radial wave. Now, what are your surfaces of constant phase in a radial wave? This is your surface of constant phase. What will be the equation? What will the equation look like? It will be a function of r, theta, and phi, or let me just work with r and theta in 2 dimensions. So this is r, and then there's some angular value theta. This is going to be a times some cosine. Now cosine of what? K times r minus omega t. Right? Assuming that these waves are perfectly circular, that is, they are completely circular, there's complete symmetry in the radial direction. I can just write this as k times r. Okay, and there will be something divided by r, because as I go further away, the amplitude of the wave will decrease. Now my surfaces of constant phase are these circles, and what is the velocity of my wave? At each point, the velocity is radially pointing outwards, right? So it's omega by k times r hat. Now you might ask, well, so again, there is only one k here, right? I'm writing kr, right? And here you might think, well, these three vectors, I have kx, ky, and kz. These are three different vectors. They are not three different vectors, okay? These are just three components of the same vector. Don't think of them as three different vectors. So if you have a velocity vector, v is equal to vx, vy, vz, right? Do you think of it as a particle moving in three directions at the same time? Or do you think of it as a particle moving in a given direction with three components? That's how you think of it, right? It's the same thing. Okay,
Okay,
so I'll stop
okay.
the recording and the